Well, good afternoon. It's 12:05 on the 13th of March 2017. This is supposed to be Cal 3, Math 227, and right now I'm the only one in the room, so don't know where the others are. Hopefully someone will be coming in soon. Let me go on and start the slideshow from the current slide, and we'll go from there. Now, we're on chapter 12, vector geometry, section 12.4, the cross product, and we had talked about before the dot product, was commutative. Didn't matter which order you multiplied. A dot B was the same as B dot A. The cross product is not commutative. But it's just not that it's not, it is actually anti-commutative, meaning it's the reverse of what you would expect. So changing direction, the order actually changes the sign, but when you think about the right-hand rule, you know that has to make sense, because if you twist point your fingers in the direction of W, cross them in the direction of V, your thumb is pointing up, say, on your right-hand rule. But if you start with the right hand pointing toward the same direction you had V going before, and then bend them to point toward W, your thumb's going to be pointing downward if it was pointing upward before. So it's not just that it's not commutative, it's exactly anti-commutative. Reversing the order changes the sign, and that's what this slide indicates. Big slide, little, lots of white space here, and this is what they call equation 4 on page 655 under the cross product. And if we use the 2x2 determinants, we can see that the signs from, if you go back one page, 654, the definition of the cross product, and the each of the 2x2 determinants there that you had for the I, the J, and the K, they show the, I think they do the K ones that they show here, because that's the direction that gets changed. You see that V1 W1 minus V2 W2, but then when you change the order of the vectors, then it's W1 W2 on the top row and V1 V2 on the bottom, and that is exactly the opposite of the determinant of the other, because your main diagonal and your anti-diagonal have switched, and so it gives you the negative sign. I was trying to see if there's anything else there. It seems like sort of a lame illustration of it, but yeah, that's what they've got here. And anti-commutivity also follows from geometric, the right-hand rule type things. We already talked about that. V cross W and W cross B are both orthogonal to V and W themselves. They have the same length, but they point in opposite directions by the right-hand rule. That's what I've already talked about, so I think that's covered. So let's move on to, this illustration here is also covering what we were just talking about. The very thing. There's the V cross W. If you point your fingers with the right hand outward toward V, cross them toward W, you're going to be pointing outward. So V cross upward, so V cross W is pointing upward. But if you start at W with your right hand, point your fingers along that of the right hand on that direction, then cross them toward V, you see you're pointing in the opposite direction. So same thing we were just talking about. There's the figure to illustrate it. Here's where I think the most important. This next theorem, there's some further properties of cross products, and they said the proofs are done in the exercises. So let's focus on these for a bit. Now the first of these is the one we just were talking about. Okay. First, the anti-commutativity rule, that W cross V is exactly the opposite, negative V cross W. And part of what we were talking about too was that a vector crossed with itself is a zero vector. Okay? And we use that in the last, I didn't say it, but they used it in their discussion at the bottom of the previous page, page 655. But I think we had bumped into that earlier as well, but maybe not. I guess we had just said it, but that's now a given here. Now, there's a part of me that knows exactly why it's given, but then I realize that part is the part that we haven't done in this class yet. Or at least I don't remember that we did. And why they haven't mentioned it. See, when I learned the cross product, I learned it by a formula first, which is similar to, but not the same as, what we used in dot products before. If you turn back to the summary at the end of 12.3, page 649, you see an alternate definition for a dot product is magnitude of V times magnitude of W times the cosine of the angle between them. And we use that a lot. They haven't given us the equivalent definition for the cross product, and I wish they had, and that's the one I keep wanting to go back to, but I can't because they haven't given us that yet. Okay, and I don't know if they're going to. It seems like they would have to somewhere here. But anyway, I'm not going to worry about that because they haven't. So how else are we going to do it? Okay. Well, if you recall, the cross product defines a plane, right? The two vectors that you're crossing define some plane, U and V, V and W, W and V, whatever. Those two vectors define a plane. And the cross product is perpendicular to that plane. Well, if you have V cross V, all you've defined is a straight line, okay? And that thing is equal, you know, just not a real nifty way to say it, except remember the cross product is a vector that's perpendicular to both of the other two vectors. Well, if you think of V crossed with itself, there's an infinite number of vectors that would be perpendicular to a number crossed with itself in a straight line, and you just can't have and if an answer there, so in one sense it almost has to be the zero vector. Now that's a pretty lame description, and I've resisted saying it, but I'm going to go on and say it. The magnitude of a cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between, and by that the sine of 0 is 0. The vector aligned with itself, the angle between it is 0, and so the cross product has to be 0. Now we didn't cover that, but indeed that's going to that is true. Number 3, V cross W is equal to 0 if and only if W is some multiple of V, lambda being the scalar multiple, for some scalar, or V is the zero vector itself. So basically it's going back to number 2 almost. Not only is V cross V equals 0, the zero vector, because cross product produces a vector, but V cross some lambda V, the lambda can be pulled on the outside, and then you have lambda is equal to V cross V, which would be 0. So that's going to be, it follows directly from number 2. Or if W isn't a multiple of V, then V has to be the zero vector itself, because that's the only way you'll get V cross W equal the zero vector, is either W is a multiple of V, or V is a multiple of W, or one of those two vectors is a zero vector itself. Okay, Roman numeral 4. And this is one I was just using before. Lambda V cross W is the same as V cross lambda W, which is the same as lambda times V cross W. Okay, so in other words, you can pull out any constant scalar from the multiple cross product of two vectors. And number 5, it's kind of a distributive rule. You just have to be careful on the order again. U plus V cross with the U is a vector, V is a vector, and W is a vector. So U plus V is the sum of two vectors, is going to be a vector. Cross W, another vector, will be a vector that's perpendicular to the plane that U plus V defines. You know, U and V have to be in the same plane. Any two vectors are in a plane in common, okay? And especially if they're not multiples of each other. And then the sum of the two vectors is in that plane, of course, too. And then if you cross that with W, you're going to be in a plane that's perpendicular both to the sum of U and V and W, okay? Well, the distributive law that this is illustrating would then say that sum of U plus V cross vector W will be U cross W plus V cross W, okay? Well, U cross W would be a plane perpendicular to both U and W. V cross W is a plane perpendicular to V and W. Well, obviously the W's are the same, so that would define a plane that is perpendicular to the sum of U and V, and sure enough, that sort of winds up making sense. And you can do them in the other order too. U cross V plus W is U cross V plus U cross W. Notice the order really matters. If you add first and then cross, then the second half of your crosses always has to be that second vector. If you cross and then add, or the vector U cross a sum of V and W, then the U is always first, cross with V and then with W. comes out being the same, but they're not equal to each other, obviously, but that's your best way of having distributive law in cross products. Okay. Now, these I'm pretty sure we've hit before. So I can't say that for certain. Let me see. Maybe not. But anyway, right-hand rule gives this to you. If you point your fingers in the direction of your right hand in the direction of the X component, the I's, cross that with J, then your thumb is going to be pointing at positive K. Okay? Now, remember I, J, and K are all unit vectors. So I cross J be magnitude of I times magnitude of J, and they're perpendicular with each other. So, and this again is using the thing I've already told you that they haven't covered in the book yet. The sine of 90 degrees is 1. So magnitude of I times magnitude of J, that's 1 times the sine of pi halves is 1, and that's equal to a unit vector K, 1. All right. So glad somebody's here. I hate talking to myself. Let's go to the syllabus here. Is anyone else coming?
Mark is coming.
Oh, yes. Okay,
Can
good.
you run to the restroom?
Okay, right. Yeah. Okay, I'll continue. Similarly, J cross K, if you cross the y-axis with the z-axis, fingers of the right hand pointing in the positive y direction, bend the fingers up to point in positive z direction, your right thumb is pointing in the positive x direction. Okay? And then you do K cross I, K pointing upward, I pointing positive x, your thumb on your right hand will be pointing in the positive j direction. Now notice what we do is keep the order in order. IJK, JKI, KIJ. The order is always the same. But, just like we saw before, V cross V was 0, I cross I is 0, J cross J is 0, K cross K is 0. Now one thing they haven't said, but it would follow, and they're going to say it in just a second in the paragraph below here, reverse the order, J cross I, and by the theorem 2 Roman numeral 1, that's got to be minus J. And K cross J is minus I, and I cross K is minus J. Okay, so that covers all possibilities of cross products in your unit vectors along the axes. Okay, so let's go to example 4, which, here is sort of a figure that might help you remembering what we were just talking about. And I don't know particularly why they chose to go clockwise. They could have gone counterclockwise and change the order of it. It seems like that would have been more reasonable in a geometric or trigonometric sense, because we just always do things counterclockwise in math, but they did this figure drawn in a clockwise manner, which is fine. It doesn't really matter. But if you list them clockwise, I, J, and K, as long as you're going in that direction, you'll get a positive result. I cross J is positive K, J cross K is positive I, K cross I is positive J. Circle for computing the cross products of the basic vectors. What I don't know is why they didn't just flip J and K down here to I cross J. This would have worked if you counterclockwise as well if you change the order of J and K. So there's nothing magical about this, but since everything else we've done in trig usually goes the other way, I don't know why they didn't do that, but that's beside the point. So let's do example 4. I do not believe they have a figure for it, so let's write on this one. Compute this. Let me get my pen darkened. All right. 2I plus K cross 3J plus 5K. Okay. Now there's several ways that you could do this. Okay. And frankly, my tendency would do it just the same way we have all the others. I know that's not what they're wanting you to do, but let's do it that way first, and then we'll come back and look at theirs. Well, what's the way we've done cross products so far? We set up the determinant, and what goes on the top row? I, J, K. All right. What goes on the second row? Yeah, the coordinates, right, the components of the first vector, the one that shows up first in the cross product. And what would that be? 2, 0. 1. Exactly. And the second vector, which will be the third row, zero, no, 3, 5. Okay? Now, how I like to do it, unlike what the book does, is lose the this wall over here and expand it. And rewrite my I to 0 and my J, 0, 3. Okay? And then do my modified, I will call it, determinant, but only do downhill diagonals. So what would that give you? You're multiplying, right? You're multiplying. I times 0 times 5. 0. Very good. The next one will be 0 again. The next one will be 6K. Okay. Now we'll do our anti, and that, of course, is a 0. This will be minus, say again, 3I. Because if you're going uphill, you're going minus, and this will be a minus 10J. Okay, so that would give you minus 3I minus 10J plus 6K. Okay, now, minus 3I minus 10J plus 6K. Got it. That's not how they wanted you to do it. Okay? Let me show you how they wanted you to. Now, it's expanding on that whole concept of distributive law. Okay? It's a lot like the foiling that we used to do, because this is 2 by 2. If this was 3 by 3 or 3 by 2 or 2 by 3, you know, just the equivalent thing to this, you do these two first. And that would be 2I cross 3J. That would be 6. I cross J is right down here. I cross J is K. Okay? So you did the first. All right, we're going to double our class size? Yes. Marcus is here. Was there something I was planning to give to you? I don't remember what it was. No, I guess it was Manuel. I was going to give something to, so yeah, forget that. Okay. Next, it doesn't matter the order here. So usually we did first outer. So what would that give you? Okay, plus 10. But I cross K, you're going the other direction. So that's going to be a minus J. Okay. So make that a minus J. Okay. Now let's do the second times the second. That would have been the innards before. Second. Okay. Okay. K cross J would be going this way, which is going
Negative.
so negative I. But how many I?
3.
Yes, negative 3I. And then the last would be these two, but K cross K is 0. Okay? Because if you go back to the theorem 2, the number 2 up there in theorem 2, V cross V is 0. Okay? So that part would give you 0. So again, you get minus 3I minus 10J and plus 6K. All right. And Faith is here. We're only missing Emmanuel, and he was out this morning. I can only figure that must mean he's sick, because he usually doesn't miss class unless he oversleeps, and I don't think he would have slept this long. Okay, so I guess he must be out. Okay, so we got the same either way. And that isn't hard. Of course, if you'd have had 2 more terms in there, it would have been a bit more involved. But you see, it's the same thing we're doing over there, okay? Basically, you know, it gives you those same results. So, anyway, that was example 4. 2 ways we went about doing that. All right, any questions on that? We're on page 656 in chapter 12, section 12.4, cross products. Getting ready to move in the bottom half of the page to example 5. I think they do have a figure here. Yeah. Sorry. Velocity in a magnetic field. Now let's see, 2 of you in physics now, right? Faith, are you in physics? No. Okay. If you've had the E&M portion of physics, the electricity and magnetism, either you're already hit this or you're going to hit it pretty soon. The force F on a proton, you tell me what a proton is. Proton. A positive charge. It's the elementary particles make up an atom. It's one of the components of a nucleus, and the nucleus is made up of positive protons and neutral neutrons. So this is a positive proton, okay, moving at a velocity of v meters per second in a uniform, magnetic field B, yes, capital B, and we usually measure that, the SI unit for magnetic field is Tesla, and that force is given by this formula. And force is a vector quantity, is equal to QV cross B. Yeah. Q times V cross B, where V is the velocity vector, V is the magnetic field vector. Okay? Now, remember, if you glance up at number 4 in the theorem 2 at the top of page 656, you'll see that lambda can go anywhere it wants to. Okay? In fact, I'm used to putting it with the V, QV cross B, which is fine. Or as the third equality there says, you can pull it outside to it, Q times V cross B. It doesn't matter. V, remember, is the velocity vector, and F is the force vector. Now, a couple of issues here. First, what if V was moving in the same direction as B? Your velocity is up the coil, or up the field. What would be the force on that proton? 0. Notice, number 3 again. V cross W is 0 if and only if V is some lambda times V. So if your velocity is this way and V is in the same direction, they are in the same direction, the cross product of that is 0. The force would be 0. They just move there and never experience any deviation. But if the proton was trying to go anywhere other than the same direction of V, then it's going to have a force on it. And V cross B, sure enough, is going to be right-hand rule in that direction. If it was over here, it would be in this direction. You know, the right-hand rule goes around that spiral like that. I can't keep it going without breaking my arm, but you know, the force is toward the center of the spiral, all the way around, all the way around. That's what gives it this helical motion, helical path here. Because your velocities, because the force is in that direction, it pulls the velocity in that direction, and as it pulls it, then the force moves too, and it keeps it moving in that helical path, going up. Now, the other deal is this has to have a vertical component too. The vertical component of the velocity, see, there's a horizontal component and a vertical component. The vertical component I would say this. If that were in the direction of B, 0 force. Okay, if it's exactly perpendicular to B, which it kind of looks like it is there, that then would just move it around in a circle. But if it's perpendicular to V but with an angle, a tilt to it, that's what gets it moving in the helical path and climbing. Okay, so don't know if that's all that clear or not, but it comes from V is equal to, F is equal to QV cross B. Okay, and that's the force in newtons. And okay, let's go back and read the problem. The force F on a proton, positive charge, moving at a velocity v meters per second with a uniform magnetic field B in Tesla, which is capital T. Now, the parameter capital T means temperature. The unit capital T means Tesla. Is F equal QV cross B in newtons, because force is measured in newtons, or capital N. Sorry. Now, the Q, which is the charge on that proton, is your elementary charge, 1.6 times 10 to the minus 19 coulombs. And you might ask yourself, isn't that the same as the charge on an electron? You're absolutely right, except the proton's a positive charge and the electron's a negative charge. They have exactly the same charge, even though the proton is 10,000 times more massive than an electron, they still have the same charge. My eyes are aching. Sorry. Okay. Calculate F if B is 0.0004 K. So the B here is 0.0004 in the K direction. Okay? That's your B down there. Okay? Q they've already given us as 1.6 times 10 to the minus 19 coulombs, capital C. Goodness gracious, my eye aches. Feels like someone punched me in it. I don't think that happened anytime. Okay. And your velocity is a magnitude of 10 to the 6 meters per second. So this is 10 to the 6 meter per second in the direction of minus J cross K. Okay. Minus J cross K. No, minus J plus K. I thought that can't be. Okay. I misread. I think that has to do with my eye. Okay. That's the direction of that 1 million meters per second. Which is flying, by the way. Okay. All right. Now, yeah, okay. This is a scalar number. It can be pulled out just like the 1.6 times 10 to the minus 19 coulombs can be pulled out. Okay? It has dimensions on it, so you just multiply those two together. But you don't need to carry this around in both of those. You could. That would be all right. Or you can just multiply this by that and pull them out, but keep the units the way they should be. So let's do that. Let's combine the two scalar quantities together. And what would that give you? 1.6 times 10 to the second? Negative 13 is what you said? Right. This is 10 to the minus 19, 10 to the minus 6. That's 10 to the minus 13. Now the units are a bit strange. Coulomb meter per second. All right. Now, that's the constant out front. What we've got here, okay, I think I left off my unit on the Tesla. Yeah, they said it, they didn't write it. I'm just going to put that capital T for Tesla. Okay, and I'm going to want some of those zeros back, I think, in a minute, but let's do the V cross B. Okay, what do you put on the top? IJK. And since we're going, we could go on and do the next I and J too if you wanted to, because you know that's how I like to multiply these. And then your V was 0 for the I, minus 1 for the J, 1 for the K, 0 for the I, minus 1 for the J. cross B, and B is 0, 0, 0004. Okay, hope you can read that. I'm having trouble focusing on it. And then we repeat those again. This is another 0, and that's another 0. Okay, now we do our cross product. That gives us a negative 0.0004 I. That gives us a 0. That gives us a 0. That gives us a, that gives us a, and that gives us a 0. So there's your answer here. Multiply that by, and I'm going to change this slightly. I'll write it as 1.6 times 10 to the minus 13 times negative 0.0004. This will be I. Okay. I had meant to write this one as negative 4.0 times 10 to the minus 1, 2, 3, 4. Since we put the other in that way, let's do that one. And this will be 1.6 times 10 to the minus 13. We'll multiply the whole number parts, and hopefully you'll see that's 4 times 16. 64, or 6.4, times 10 to the, add the exponents here, minus 17. Oops, my pen drug. Okay. Goodness gracious, I had it. I'm just feeling dizzy. I don't know why. So 6.4 times 10 to the minus 7 I, and that should wind up in newtons. Okay. Now, I don't know if you know where those newtons come from. You don't need to worry about it. Just know that forces come in newtons. Your velocities in meters per second and your B in Tesla, but if you broke Tesla down to its fundamental units and then mess with them, you would see that does come out to be units, newtons. So we'll just take them at their word for it that it is. Let's see if that's Oh, forgot this one. I had paused at the beginning to think about it, and thought the better of it, and now I'm guessing. Oh wait. Okay. What they, I had thought we could just pull this out and multiply it here. And just let these take care of themselves in our vector multiplication, cross product multiplication. They don't seem to want to work that way well, and what we probably should have done was leave this in with these. make this a 10 to the minus, negative 10 to the minus 6, that a positive 10 to the minus 6. It still does the same thing. That's where the problem comes in, is that there's a component here of the square root of 2. But I can't see why the vector multiplication doesn't take care of that. The cross product, it seems like it should. And I don't see anything wrong with doing this way. That's why I worried at the beginning when I was pausing to see, can I really pull that out? Because this is supposed to go with this one, it's supposed to go with that one as well. But then it would seem like to me that you would then just put that in here, that in there, do the same thing, and you still just get this multiplied by that, which is exactly what we did. And I'm not seeing why that doesn't work. But they're saying that the, oh, wait a minute. Nope, I included that. They're saying this vector here, minus j plus k, has a length of square root of 2. Now, I agree with that, okay? As long as you don't multiply it by the 10 to the minus 6. I'm sorry. Yeah, 10 to the 6 meters per second. Oh, that's it. That's it. Sorry. I didn't read. The magnitude of the velocity vector is this. It's not this times this. The magnitude of the velocity vector, v, is this. Okay? And that doesn't multiply by this. That multiplies by the unit vector of those, and to get that unit vector you would have to divide by root 2. That's where it is. I had just read it too quickly. Yeah, the velocity and the uniform, okay, in which v has a magnitude of that in the direction of minus k, j plus k. Sorry about that. When I wrote it down, I thought it meant is this times that, and it's not. This is the magnitude of this thing, of the velocity in this direction. But what is that direction? That would be the unit vector in this direction. The unit vector in that direction would be, minus j plus k. Now, you can't see this. The j goes along like this, and the k is like this. Minus j plus k. This right here, the magnitude of this is 10 to the 6th meters per second. But the j cross plus k, and the scale looks really rotten here, but if this is j minus j and plus k, then the length of that, the vector along that way would be like they said, if this is minus j, that's plus k there, minus j plus K here, then the length of that would be of the unit vector in that direction would be here, but it would be divided by root 2 because the square root of this square plus that square would be square root of 2 here. So that's why you divide by root 2. Okay, sorry about that. So this divides this by the square root of 2. That divides that by the square root of 2. Okay, and that, I think, gives you the same thing they got there. Okay, and there's a minus sign in front. Minus I, because that minus sign carries. Sorry about that. Okay, and 6.4 divided by root 2, 1.414, what does that give you? Should give you the same thing they got here. Minus 6.4 divided by the square root of 2. Yeah, 4.5 approximately. 4.5. Okay, we'll round to 4.5 times 10 to the minus 17th. I. And that would be newtons. Okay. Sorry about that. When I first started, I said, now is that what multiplies by that? And that's how I read the problem, but that wasn't what it was. That's the magnitude of the sum of those two vectors. So you have to get the unit vector in that direction. That would be divided by root 2. Okay. Sorry. Okay. Let's move on to cross products, areas, and volumes. Okay. Cross products and determinants, which you use to get the cross products, they have special meanings. And if any of you had taken I think it's linear algebra. No. Is that right? No, I don't think linear algebra deals with cross products much. But if you've messed with them before, the cross products and those determinants are closely related to areas and volumes. Let's say we have a parallelepiped. What does that mean? A parallelepiped. Well, this is a picture of it. If you have U, V, and W here, three vectors. Okay. And they form what they call a parallelepiped. Now, nothing there of those three vectors has to be perpendicular to anything with each other. Okay? But here's U going up this way, V here and W here. Those could be any angles between any two of them that you want to have. Nothing has to be perpendicular. But if you were to draw the parallel vector here, here, and back here to V, a parallel vector here for U, here, here, and there, and a parallel vector for W here, 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 and here, then you make a figure they call a parallelepiped. Where is the parallel coming from? All the sides that are along V are parallel to V. These four sides here are parallel to V. And for U, this one, this one, this one, and that one are parallel to U. And for W, this one, that one, that one, that one are parallel to W. So everything's parallel to each other. Now, if these were all 90-degree angles, that would be a rectangular parallelepiped. Okay? And we could do its volume, length times width times height. Okay? But with these not being right angles there, none of them, or none of them have to be, then how do we get the volume of that parallelepiped? Okay? Well, let's back up a step. Let's go back to the parallelogram, which is V cross W. Okay? Okay, I'm sorry. V and W. okay? How do you get the area of that parallelogram? Well, here it is. I knew they were going to have to show it somewhere here, and they have finally, okay? What I haven't figured out is why they didn't come up with this earlier, okay? But here it is, what I told you before. Another definition for cross product of two vectors, v and w, as long as they're not collinear and neither one of them is a zero vectors, is the magnitude of v times the magnitude of w times the sine of the angle in between. Okay? With that in mind, then, if you cross v cross w, okay, well, v cross w is going to be the sine of this angle here is going to be this side here. Well, let me put it this way. Sine of this angle here is going to be h times the magnitude of w. Okay? Because this is the right angle here. That's the hypotenuse. That's the opposite side of that angle theta. So the area of this parallelogram is the magnitude of v times the magnitude of w times the sine of the angle between. Okay, I don't know if you remember this. Okay. You might remember this, you might not. This, okay, I'm going to have to shrink to show this. Hopefully that's not too small. Okay, if we were to draw a line parallel to our h there, okay, then this triangle is just like that one. This length is that length. This h is the same as that h. This angle here, this line hypotenuse is the same as that one. Those are all the same. So that's the same little angle there. Well, the magnitude of v is this little piece plus that little piece. And this piece is common, so this piece and that piece are the same. So these two are the same. So that's the length. This is the width. Length times width is height. This area is the same as that area. That's the area of the parallelogram. Okay? The length, the v length times w times the sine of the angle theta gives you your h. Length times width, v times h. That is the area of that parallelogram. Okay, now, the cross product, they have it backwards, don't they? Yes, they do. Yeah. V cross w, right-hand rule, that would be coming this way. They have this arrow in the wrong direction. Okay? They have it that way. That would be w cross v. So why they have that backwards, I don't know. But it doesn't really matter too much here. That is perpendicular both to w and to v. Okay? It really should be coming out this way, but that, I don't know why they drew the red line backwards. Did they do it in? Yep, they did in the new version too. Unless I've lost my mind. That's right-hand rule, that's right. Okay. That doesn't really matter. By the way, the area of that parallelogram is the magnitude of that length. That's what that tells you. Okay. So let's step it up a notch. And the v cross w is the area of this base times the dot product with the u. Well, what is the dot product with u? That is the cosine of the angle theta, which would be this. Now this h here and this h here are not the same h's. I wish they'd have used something else. But that is this height here. And now this is perpendicular to that plane v cross w. So it's perpendicular to that. This pink line is. And the u dot that is going to be exactly the volume of that parallel height. Okay, So the sine of this angle gives you that h. The cosine of this angle gives you this h. Okay? And the area here, which you get from here, v cross w, or u cross w cross v, it doesn't matter. It's just the magnitude you're interested in. Dot that with this one, and that gives you component of u along v cross w, and that's going to be u times the cosine. The angle here, that would be this one right here, and that then makes a volume that is equivalent to here. Now, that's a lot harder to show because now you have to draw a three-dimensional figure here that this is the same as the angle you would get here, you know, and you chopped off this and added it there, which I don't want to try to draw that, but that does give you the volume. Okay, so what's the bottom line to this? And my word, what they do is go down to the bottom of the page and show the math before they show the areas, okay? In other words, the two area formulas that are in your book on the middle of page 657, not yours, Silva, but the others, they left them off of this one. So let me go back and fill in the blanks here, okay? This area of the parallelogram here, so the area of the parallelogram P, and this is the parallelogram P right there, is equal to the magnitude of V cross W. Okay. Only trouble is they drew it in the wrong thing, but the magnitude is the magnitude. Okay. It doesn't matter which direction it's facing. Okay. I just now noticed they have something different here. The area of this triangle here, which is the triangle that ends at V and W, that triangle is exactly half the area of that parallelogram. So the area of the triangle, and that's this triangle here, okay? That would be magnitude of V cross W over 2, exactly half of it. That's the block they left off the slide set in the new book. Your book doesn't have that in here, okay? Next, they consider the parallelepiped, and this is figure 10 in the new book. So these two are figure 9, and this is figure 10. Okay, and that's the parallelogram. And when you talk about the volume of that, you get that parallelepiped, volume of the parallelepiped. Now, here's what they do with that. They first show what they mean by U dot V cross W. That would be U dot, and this is from the formula. If you've done the IJK, what they're using for V is V1, V. A1, B1, where are the vectors listed? Okay. All right. Again, the two books are disagreeing. Okay. And I'm glad they are. I'm glad the new book did it better. Okay. What the old book called U was A1, B1, C1. okay? They're calling it U1, V1, U1, U2, V2. Okay, so I don't know if it's worth it or not. This is U1, U2, U3. Earlier in a problem I wondered, why in the world did they use what they did? This will be V1, V2, V3. This will be W1, W2, W3. All right. Now, so this should be V2, V3, and this should be W2, W3. This should be V1, V2, W. Second?
You could read the C, C is W.
Okay. What they did in your, okay, let me write down what this one's based on, because you don't have this in yours. Vector U is our components U1, U2, U3. I bet you in your book it was A1, B1, C1. So you see they changed the letter and they changed the subscripts. So that's why it's totally different. V is equal to V1, V2, V3. I don't know if you remember, but last time we met, I asked, why in the world did they change these? And I don't know why. That was an awkward way to do it. And W, this makes so much sense. These are the components of W. W1, W2, and W3. You don't have to keep up with who's 1, 2, and 3 and who's A, B, and C. Just do it by that, okay? And if you had V cross V, V cross W, this is I, J, K, V1, V2, V3, W1, W2, W3, right? Those are the components. Do your, repeat the I and the J columns, V1, W1, V2, W2. Then do your multiplication. This is V2, W3 minus W2, V3, I. Okay? You subtract those two. Okay? And then the J's are V3W1 minus V1W3 J plus V1W2 minus W1 V2 K. Okay? Those would be your vectors, and basically that's what they've done here. If you'll notice, this is V2W3 minus W2V3 I. V1, and as I was putting this, would be a W2. This is a V2, V3, and this is a W2, W, no. V1, V2, and W2, yeah. Yeah. And then you just have to do that with them all. And this is the I component of U would be U1 times the I component of the cross product would be that one, not this one, but this one. So this is the U1. This is U2, and this is U3. Okay. Here's the one difference. They put a minus in here, and that's because what I call, those are threes there, not twos. That's a 3 and that's a 3. Oh. Yeah, that should be 2s and 3s, 1s and 3s, 1s and 2s. Yeah, that's right. I put this one first, that one second, because of the minus, but it all works out. Okay. Now, then you put these all together, and that puts the U1s on top, and it's multiplied with this, U2 multiplied with that, U3 multiplied with that, just like this does. So that gives you the determinant of UVW. Okay. And it's pretty obvious here. That's vector U, that's vector V, that's vector W. Okay? Just like it says. And that then gives you a way to calculate the volume of a parallel pipette. Okay. Rationalizing the two books, that's the two additions. So this is your theorem 3, which is theorem 3 in both. Yes, sir?
Real quick, I'm sorry, I'm trying to figure out if you have the teacher's edition for the new 090, 098 that we're rolling out.
I don't have anything on the new 03, 98.
Dr. Pruitt may have that, because I should be creating a course, a code requisite course with 100 for the 098, and I need a text.
Okay.
Try to see
He might. You can give him a call and see.
Okay,
I'm pretty sure nothing's come to me. You might try Miss Martin down the hall here.
Okay.
And I would have said, because you've been teaching.
Well, so we just rolled out the 090 this semester, and we'll roll out the 098.
Oh, that's right.
Summer, I think.
Yeah, but
I didn't have the 090 this semester, so I didn't get it.
Oh, you didn't have any of it. Check with Miss Martin. She would be the best one. She probably only has one, but she might let you borrow it,
Okay.
And then Dr. Pruitt also.
Okay, all right, thank you.
Sorry. Sorry, I didn't. Okay. Where did my cursor go? Okay. Now, here's theorem 3. Oh, I know what. That's why it was up there. I was going to zoom it. Okay. The area and volume via cross products and determinants. If U, V, and W are non-zero vectors in R3, just like we've had them being, the parallelogram P spanned by V and W, the last two there, okay, that forms a plane, and the parallelogram in the plane has an area of magnitude of V cross W. Done. We did that before. We showed the geometry of that. The parallelepiped, capital P, which, why is that molded in a capital P, I'm not really sure, spanned by U, V, and W, then has the volume of U dotted with, okay? Now notice here they put the bars here, meaning the determinant of. No, I'm sorry. This book doesn't mean that. This book means the absolute value of, because a volume can only be positive. This could give you a negative number, so once you've done the calculation, if it comes out negative, change the sign to positive. If it comes out positive, you got the answer. So this is absolute value bars. Now, Marcus is taking linear algebra. And this morning in linear algebra, we said the absolute value bars means determinant. Not in this text. this text absolute value bars means absolute value, and the DET means the determinant. Okay? But the determinant that you do here is of vector U, which is U1, V1, U1, U2, V2, U1, U2, U3, V is V1, V2, V3, and W is V. Yeah. And you take the determinant of those and then take the absolute value of that answer. Okay. So, the one time I guess you have to use the DET for determinant is when you're combining that with absolute values. Okay. Which is what we're doing right now. Okay. So let's go to example 6. I think this is the figure for it. In the new book it's figure 11, but in the slide set it's figure 10. Okay. Okay. V is the vector 1, 4, 5. W is the vector -2, -1, 2. Okay. And it says to calculate the area A of the parallelogram spanned by V and W. Okay? How would you do that? It's the area of the parallelogram. I can't write. It won't come up. There it comes. Okay, let me try it one more time. Of the parallelogram. Okay? There they're showing. It's this one right here. What's the area of that parallelogram? Magnitude of V cross W. Okay. And how would you do that? Set up your determinant. And I like to modify that determinant by putting the extra 2 columns in there. And the one that's listed first, V, we'll put here 1, 4, 5, 1, 4. And W is -2, -1, 2, -2, -1. Okay? And then do the diagonals. And you would have that would be an 8 plus 10 is 18i. No. Oh, sorry. This is what you get from writing sloppy. Don't write sloppy. Okay. Sorry about that. Let me go and erase this and erase that. Okay. It's this one. Okay. Plus 5. That would be 13i. Okay? You see? The main diagonal down minus the backward diagonal. I just got off. Okay? And then if we did the main, I'm going to erase those so there won't be so many lines in there. So let's erase those 2. Now let's do the J ones. That would be a -10 -2, which is -12J. Okay? And then the K ones, K's are a little strange, and you don't form a little X like you did before, but your main diagonal down would be, yuck, my pen didn't catch up. That was a 1 there. Okay. It was -1 plus 8 equals 7K. All right. So that's your U cross V. I mean V cross W. Okay. So we want the magnitude of, get the right order, 13I minus 12J plus 7K. Okay, and what would that magnitude be? The square root of 169. Yeah, 13 squared. Is that right? Right? Plus 144 plus 49. So let's see what that adds to. That's 208, and 144 would be 352. Huh? 362? Okay. 362? Okay. I'll trust you on it. Square root of that would be what? Oh, let's just leave it around 19. Okay. Around 19. Yeah, that's what they did too. Approximately 19. That's the area of the parallelogram. Okay. The vertical leg of the parallelepiped is the vector 6K. The vertical leg of the parallelepiped is 6K. Where in the world did they get that? Okay. They didn't give us a vector u, okay, anywhere in the problem here, okay. They just gave the picture, and this is then u is here. So basically u is equal to 6K. Strange the way they did that, okay. Okay. Oh, okay. Now I see. The part B says, calculate A, we did. B, the volume of the parallelepiped in figure 11. So you had to look at the figure, and this is figure 11 now, and that figure shows that that vertical leg is 6K. So your U is the line 6K, okay? Now, we've got to dot that with our V cross W, okay? Well, we just had our V cross W. So here we have, what we call this, volume of P. I'll put a bold over it just to let it, it's a P. The volume of that P is going to be 6K dotted with what we just had, 13I minus 12J plus 7K. But guess what, folks? I mean, that's our V cross W. Okay? 6K is 0, 0, 6. And when you dot those two, 0 times 13 is 0. 0 times minus 12 is 0. And this would be 42. Okay? That's the volume. Okay? And that's it. Whatever your units are, 42 cubic units, whereas your earlier thing was 19 square units. Okay. Now, the next topic we're hitting here, we can compute the area A of a parallelogram, this parallelogram, spanned by the vectors V and W. Now this is in the xy plane. So the vector V is V1, V2, no Z component. Vector W is W1, W2, no Z component. Okay? Now, again, in your book, they have A, B, and C, D, which is useless change of thing. We usually call this V1, V2, and V3 happens to be 0. This is W1, W2, and W3 happens to be 0. Okay? Now, we can compute the area of a parallelepiped spanned by these vectors, V1 and V2, okay, with 0 components in the z direction by regarding v and w as vectors in R3 with 0 components in the z direction. That's what I just said. Thus, we write v, we've already done that, v1, v2, 0, w1, w2, 0. The cross product then would be what? The A here, the area here, would be the cross product of magnitude of the cross product of V cross W. And how do we do that one? I, J, K, and this would be V1, V2, 0, W1, W2, 0, and if you extend 2 more, J, V2, it's I, sorry. I, V1, W1, and J, V2, W2, okay? And you do this, I component 0 minus 0. That's not lining up well, but that's what you get. That's 0. J is 0 minus 0. That's 0. Your K is V1, W1 minus W2, yeah, I'm sorry about that, minus W1, V2, okay? This is the K component, and that's the only component, okay? So the area would be exactly that, okay? V1, W2 minus V2, W1, doesn't matter which order you multiply. And that gives you this. Well, it doesn't quite. Yeah, it does. VW, the determinant of VW, and that would be the determinant of V1, V2, W1, W2, which would be V1, V2, W1, W2, and that would be V1, W2 minus V2, W1, or whichever order you want to write them. Okay. And we put absolute values around them because areas are always positive. Come up with a negative, change it to positive. All right. So let's do example 7 then. I think this is the figure for it. Compute the area of the parallelogram in figure 13. In your text here, this in the slides, it's figure 12, so I'll change it to a 13. And here we have V is 1, 4, and W is 3, 2. Okay, they got that part right. Okay, so compute that area. Well, what did we just say it was? That area is equal to the magnitude of the determinant of the symbology gets to be a pain. 1, 4, 3, 2. Okay? What would that be? What's the determinant of that vector? Minus 12, be negative 10, and then take the absolute value, that would be 10. That's it. Okay, 10. Absolute value of 10. I went on and did it. Okay? Now, we now derive the properties of the cross products listed in Theorem 1, which was back quite a ways. Now, how are we doing on time? 5 minutes? Yeah. Okay. See what we can get done here. Theorem 1 was way back. Page 655. geometric. Ah, there it is. I kept missing it. I knew we had to have had that. There on number 2, V cross W has a length of magnitude V times magnitude W times the sine of the angle in between. I knew we had to have had that. Okay. So what we're going to do here, it says, is prove those cross product properties. The 3 there in theorem 1. That V cross W is orthogonal to V and to W. V cross W has a magnitude of magnitude V, magnitude W, times the sine of the angle theta in between. Theta always either acute or obtuse, but never greater than pi. Okay? And that V, W, and V cross W form the right-handed system. Okay. So, how are we going to start this? Let's see. Man, where in the world is this? Oh, there it is. That's equation 11 at the bottom of page 658. Okay, I think I'll blow this up because I'm not going to spend a lot of time on this. We've already spent too much time, probably. Okay, here's your cross products. V dot V cross W. Okay, I guess before we begin, I should have done this earlier. I started to, but I was trying to find where that picked up. Here's vector V is V1, V2, V3. Okay, and vector W is W1. Okay, W2, W3. Okay. Now, I've got to go in and change this. This is V1. This is V1. This is V2, I think. This is, that's not right. No. Okay. This is V2, V3, W2, W3. This is, I'll leave the minus sign for now. I don't like it. V2, V1, V3. This is W1, W3. V3, V1, V2, W1, W2. Yeah. Pretty sure that's how it's supposed to be now. Boy, what a pain in the neck. They can't do that right. Okay. So, that's what your equation 11 is. Okay? Believe I've got it right now. Okay? Straightforward algebra. Carry it through. Multiply the things out. Basically, that's V1, V2, W3 minus V1, W2, V3 minus V2, V1, W3 plus V2, W1, V3 plus V3, W1, W2 minus V3, W1, V2. Okay, just multiplying those things out, taking them, dragging them along there, shows that the right-hand side of equation 11 is equal to 0. Whoa! Let's see why that is. Here's a V1, V2, W3 minus V1, V2, W3 from there. That adds a 0. Here's a V1, W2, minus V1, W2, V3 plus V3, V1, W2. Yeah, those add to 0. So both of those add to 0. We already got one of these out, and we've got a plus V2, W1, V3 minus V2, W1, V2. Yeah, sure enough, those two add to 0. Slug through it and you got it. Okay. How are we doing? Time. Let me just show the next slide. Okay? The cross product of U cross W squared is, yeah. You know what? I'm just going to say the rest of this may be interesting, but I don't think it's all that useful for what we're going to be doing in the future. So let's just say we finished 12.4. You want to go over those preliminary questions or not? We can do it next time at the beginning. Huh? Next time at the beginning. So we'll start that and then move on to 12.5. Planes in 3 space. I think that's a lot more important than some of this theoretical stuff here. So I'm sorry, I probably took too long with this today, but I did want to show you how some of that worked. But then I didn't realize the slideshow and the book were using different nomenclatures, so that took half of our time. Sorry about that. Okay, and we'll pick up then and do 12.5 next time. Good deal. Be working on those tests. I don't know if I had mentioned this before. I've gotten 2 of the 4 of you have turned in your papers, and 3 of the 4 have turned in your first test. So that's good. We're soon going to have the second test, so it'd be good to go on and get the first test and the papers, make progress on the papers and get the first test done. Good deal. We'll pick up, and we won't even leave off there. We'll start